Okay, so L'Hopital's rule. Basically, we already covered limits in order to be able to evaluate derivatives. And now we're going to use derivatives. Now that we've learned how to do a few derivatives, we'll use those to evaluate some limits that we might have found difficult before. Okay, so first I'm going to give you a plausibility argument for the rule. It's not really a proof, but at least maybe it makes it a bit more believable. Okay, so here's a problem. Supposing that I have a function f and a function g, and in the limit f of x goes to 0 as x goes to x naught, and g of x goes to 0 as x gets very, very close to x naught. Now, if I want the quotient of those two things, right? So I'm taking the limit as x goes to x naught. Now f of x is going to 0 and g of x is going to 0. And so if we naively, just without thinking, if we just plugged in the values, we would get 0 over 0. Okay? So when I write 0 over 0 in square brackets like this, that's a notation that means that if I just did a substitution, if I tried to evaluate the limit by doing a substitution, just doing the function evaluation, it would look like 0 over 0, which we know doesn't make sense. But this is the form that you would get if you tried to do a substitution. Okay. Now, L'Hopital's rule is a way of not always, it can't always help you, but many times it can help you when you get a form like this. Okay. So here's the argument. Supposing that I have f of x, and we're going to evaluate the limit near 0, near x naught. So we'll let x equal x naught plus h, and we're going to let h get small in order that x gets to x naught, and we'll let g of x equal g of x naught plus h. Now, if the function f is differentiable at x naught, then our linear approximation looks like f of x naught plus h is approximately equal to f of x naught plus h times the derivative of f at x naught. But f is going to 0 at x naught, so we drop that. So you would get f of x is approximately equal to h times the derivative of f at x naught. And similarly, if g of x is going to 0 at x naught, then yes, this is a question.
Here h is a very small question. H is very small over here.
Yes, h is very small. Right? So we're assuming that we're getting very, very close to x naught by allowing h to go to 0. Okay, and similarly, g of x will be approximately equal to h times g prime of x naught if g of x naught is equal to 0. Okay, so what is the quotient? Well, the quotient should be approximately equal to h times the derivative of f at x naught divided by h times the derivative of g of x naught. And then the h's would cancel, and that would give you that f of x over g of x, if f is 0 at x naught, and if g is 0 at x naught, and if f is differentiable at x naught, and g is differentiable at x naught, then f of x over g of x is approximately equal to the derivative of f at x naught divided by the derivative of g of at x naught. Okay, so that's my justification. Now we'll apply the rule. Okay, so this is for the form which we write as 0 over 0 in square brackets. That means that if I put in x equals x naught, then the numerator function goes to 0, and the denominator function would go to 0. Okay? So here's the rule. If f and g are differentiable at x naught, and f of x naught equals 0, and g of x naught equals 0, then the limit as x goes to x naught of f of x over g of x is equal to the limit as x goes to x naught of the derivative of f at x divided by the derivative of g of x. So once again, if f goes to 0 at x naught and g goes to 0 at x naught, then instead of, and you would have the form 0 over 0 with a naive substitution, then you can instead evaluate the limit as x goes to x naught of the derivative of f divided by the derivative of g, if this second limit exists, right? So L'Hopital's rule is not necessarily guaranteed to help you out, okay? But a lot of time it can, okay? All right. So let's try. Okay, just one warning before we start. There are two forms for which L'Hopital's rule works. One form is if you would get 0 over 0 with a substitution. The other form is if you would get infinity over infinity by a substitution. L'Hopital's rule can help you with other things, but then what you have to do is you have to manipulate things until you get into one of these two forms. You cannot use it with other forms of limits, okay? All right, so let's do an example. The limit is x goes to 0 of 1 minus cos of x over x squared, okay? What would a naive substitution give you? If I put in x is equal to 0, I would get 1 minus the cos of 0.
0 over 0.
Cos of 0
over
is
0.
1. So you get 0 on the top.
Rule is
And at the bottom, you would get 0 squared, which is 0. All right? So when I write 0 over 0 in square brackets, that means that if I were to put in x is equal to x naught, which is 0 in this case, I would get 0 in the numerator and I would get 0 in the denominator. So I have a form that can be tackled by L'Hopital's rule. So L'Hopital's rule says, instead of trying to evaluate this limit, I can instead try to evaluate the limit as x goes to 0. All right, what's the derivative of 1 minus cos x? It's sine of x, right? It's 0 minus sine of x, which is sine of x. And what's the derivative of x squared? It's twice x. Now this is a limit that I can do. Well, is it a limit that I can do? Well, no, not yet. This would give me sine of 0, which is 0. And this would give me 2 times 0, which is 0. So once again, I would have a problem. So then I can do L'Hopital's rule twice. So I can say,
Sir, cannot we use the squeeze theorem here?
sorry, you have to say that again?
Sir, cannot we use the squeeze theorem here?
Yeah, there might be several ways of doing a problem. I'm just showing you one particular way of doing it, okay? All right, so this would be the limit as x goes to 0 of cos of x over 2, right? And then that limit you can evaluate as 1/2. Okay? I probably should have written out that step here. I'm sorry about that.
So can you please explain this thing again about the second L'Hopital?
Right. The limit as x goes to 0 of sine of x over twice x. If I put in x equals 0, then the numerator goes to 0 and the denominator goes to 0. So this is once again this 0 over 0 form, okay? So then I would do L'Hopital's rule again. And when I do L'Hopital's rule again, I get the limit is x, this is the same as the limit as x goes to 0 of cos of x over 2. Now, what's the limit as x goes to 0 of cos of x over 2?
Oh, yes, I got it, sir. It's 1/2.
1/2. Yeah. So sorry about that. I dropped a step here. I'll revise that in the notes. Okay. So
Sir, so can we use it as many times as we want to get our required answer?
yeah, that's
L'Hopital's
right.
rule?
That's right. And so what you'll sometimes see is if you had, say, an x cubed, right, in the numerator, in the denominator, then you'd apply L'Hopital's rule and you'd get something times x squared. Then you'd apply it again and maybe you get something times x. And you could just keep doing it until the denominator isn't giving you any more problems, right? Okay, so again, here's an example where it's used twice. The limit as x goes to 0 of x to the 4th over x cubed plus x squared. If I put in 0, x is equal to 0, I would get 0 to the 4th, which is 0. So the numerator would go to 0. And the denominator would be 0 cubed plus 0 squared, which is 0. So I would also get 0 in the denominator. So then I write in square brackets 0 over 0. And what I'm saying is that this is of the form 0 over 0. This is one of the forms that L'Hopital's can help me with. Okay? So then I'd say, okay, that's the limit as x goes to 0 of the derivative of x to the 4th is 4x cubed. So I replace the numerator by its derivative. And the derivative of the denominator is 3x squared plus twice x. So I've replaced the denominator function by its derivative. Okay. Now, it's still not something that I can do directly, but what's happened is that the degree of the polynomials that we have in our problem has been reduced. Okay. So again, the second limit would again give me 0 over 0 if I tried a substitution, but that's a form that can be tackled by L'Hopital's rule, so I apply it again. So then I get the limit as x goes to 0. Yes, there's a question?
Yes, sir. We are applying L'Hopital's rule to evaluate the limit, right?
Yes,
We're just doing this to get our answer by evaluating the limit.
that's right.
Okay.
Okay, so now the derivative of 4x cubed is 12x squared. So I replace the numerator by its derivative. And the derivative of 3x squared plus twice x is 6x plus 2. And so I replace the denominator function by its derivative. Now the limit as x goes to 0 of this is easy. The numerator goes to 0 and the denominator goes to 2 when I do a substitution, right? So it's 0 over 2, which is equal to 0.
Sir, we'll apply this rule until we don't get 0 over 0. Even if we get a constant in the numerator or denominator, we'll stop applying this rule, right?
That's right.
Okay.
Right. Once you stop getting 0 over 0, you're not allowed to apply the rule anymore. Okay? Okay. Now, of course, this is one technique, but unless you're told to use L'Hopital's rule, you don't have to use L'Hopital's rule, right? Okay, there's a question?
Sir, what if we get something over 0?
No, that's not a form that L'Hopital's can handle. What you might do, we'll see an example where you can manipulate the function a little bit, do a little bit of algebra, so that L'Hopital's can work with it. But unless you have the form 0 over 0 or infinity over infinity, you're not allowed to use L'Hopital's rule. Waleed has a question?
Yes, sir. Sir, I wanted to say that instead of L'Hopital, if we use the simple method, we could get the answer quite easily. So
That's right.
L'Hopital is not a shortcut.
That's right. L'Hopital's is not always a shortcut. So as you say, there's an easier way to do that. And sometimes another approach is more efficient than using L'Hopital's rule. Yes. Okay. So what would we do here? We'd probably divide by x squared, right? And that would give us something that we could evaluate directly.
Yeah, you would get x squared over x plus 1.
Yeah. So
So,
that would
sir,
work. Right.
whenever power of the numerator is greater than the denominator, we will always get a 0.
Probably, yeah. Okay. All right. L'Hopital's works for directional limits. So if the directional limit will give you 0 over 0, then L'Hopital's might also help you. And doesn't always, but quite often. So limit as x goes to 1 from the right of x minus 1 over the root of x minus 1. Okay. And you know, the way we've seen it before, we could maybe factor root of x minus 1, or we could multiply by the conjugate root of x plus 1 on the top and the bottom. Those would be other ways of doing it. But let's say that we wanted to use L'Hopital's rule. So first of all, am I allowed to use L'Hopital's rule? Well, yes, I am, because if I do a naive substitution, I put in x is equal to 1. The numerator goes to 0 and the denominator goes to 0. Okay, so next to the limit, I write 0 over 0 in square brackets to indicate that I have picked that substitution, naive substitution would give me a form that L'Hopital's rule can handle. Okay, and then so the limit, that's if we apply L'Hopital's rule, limit as x goes to 1 from the right, the derivative of x minus 1 is 1, and the derivative of root x minus 1 is 1 over twice root x. Okay. Replace the numerator by its derivative, replace the denominator by its derivative. Now we've got this 1 over something, so we get twice root x. Now that's something that you can do by substitution. You put in x is equal to 1, twice the root of 1 is equal to 2. So any questions about that? Okay. As I said, so two forms that L'Hopital's can help you with. One is 0 over 0. The other is infinity over infinity. Okay. We're not using infinity as if it's an element of the real numbers. Okay. Just means the first term would become unbounded and the other term would become unbounded. So the rule is that as x goes to x naught, f of x, let's suppose that that would go to plus or minus infinity if you naively plugged in x equals x naught. G of x is the same. If you naively plugged in x is equal to x naught, g of x would go to infinity. Now you're concerned with the limit as x goes to x naught of the limit as x goes to x naught of f of x over g of x. That can be replaced. Yeah. That can be, yes?
Is it positive infinity?
It could be positive infinity or negative infinity. It doesn't matter.
Okay.
Okay, so that you can replace that by the limit as x goes to x naught of the derivative of f over the derivative of g, again, provided that the second limit exists. Okay, so let's see an example. Let's say we want to evaluate the limit as x goes to infinity of x squared plus 1 over 1 minus x squared. Again, we've seen other ways of doing this, right? We could just divide top and the bottom by x squared. That would be another way of doing it.
Negative infinity.
Right, right. But let's use L'Hopital's just to have an example of L'Hopital's rule. Okay. So the limit as x goes to positive infinity of x squared plus 1 divided by 1 minus x squared. Okay, so the top, as x is going to infinity, x squared plus 1 is going to infinity. And as x goes to infinity, 1 minus x squared is going to minus infinity. So this has the form infinity over infinity. You write infinity over infinity in square brackets next to the limit to show that you've found that you found this form that L'Hopital's can help you with, and now you intend to use L'Hopital's rule to do the problem. Okay.
Sir,
Yes?
sir, can you go back to the previous slide?
Yeah.
Sir, it's a visual.
Okay.
Sir, what is second limit here? Second limit exists.
Yeah. So the second limit is the limit using the derivatives.
Oh, okay.
Okay.
Second derivative.
Yeah. Okay. So where are we? Okay. So we apply L'Hopital's rule. Limit as x goes to positive infinity. Yeah, Fatima has a question.
Yes, sir, you said that it's a second limit, so we're implying that that is the first limit. What's the first limit?
Yeah.
Is
So
that
the first limit is you were trying to do, that was the one that would give you the form infinity over infinity, right?
okay? So, would we actually consider it as a real limit?
Yeah, so if you have something like this would give you the form infinity over infinity. And L'Hopital says that, well, you can try doing the limit of the derivatives instead, the quotient of the derivatives instead, right?
Sir,
Yes.
so
Okay.
my question is that if we like make one minor change in this question, like we're not moving towards a positive infinity, rather we are moving towards a negative infinity, then how is going to like this change going to affect our answer?
L'Hopital's will still work. Okay. If you get minus infinity over infinity, or if you get infinity over infinity, L'Hopital's work in both cases. Okay.
So, but I don't think so there will be any change to the in the answer.
Well, I don't. Yeah, and in this case, there wouldn't be any change, right? Because of the
Okay.
square, right? Okay, so limit as x goes to infinity of x squared plus 1 over 1 minus x squared. The numerator would go to infinity. The denominator would go to infinity. So you write infinity over infinity in square brackets to show that you understand that. This is something that L'Hopital's might possibly help you with. And now you're going to apply L'Hopital's rule. So this is equal to the limit as x goes to positive infinity. Derivative of x squared plus 1 is twice x. The derivative of 1 minus x squared is minus 2x. Okay? So now you have
Sir,
yes?
sir, didn't we at some point assume that infinity over infinity is equal to 1?
No, we didn't.
And not in this lecture, but before, like, do we assume
No,
that?
no, we can't. We can't.
Okay.
Okay, so this gives us 2x over minus 2x. And so now we do the usual thing. If I see if I see a common factor on the top and the bottom, I divide it out. As long as I'm not dividing by 0, that's perfectly fine. And so this is the limit as x goes to positive infinity of minus 1, which is minus 1. Okay. So is this one okay? All right. So other forms, okay, this rule only works for these two forms. If you get another form, then we have to manipulate things in order to get to something that L'Hopital can help us with. Okay, so later on we will see forms that look like 1 to the infinity or 0 to the 0 or infinity to the 0, things like that. Okay, you cannot apply L'Hopital's to a problem until a substitution would either give you 0 over 0 or infinity over infinity. So we're going to see how you can manipulate something so that you can get something that L'Hopital might be able to help you with. Okay, so let's do some examples. Limit as x goes to 1, sine of 2x squared minus 2 divided by sine of 3x minus 3. Is this some, if I put in x is equal to 1, what will I get?
So can you
0.
0 by 0.
Yeah, I'll get 0 by 0. So I would get 0 by 0. So that's a form that I can
Solve with Hopital's rule.
attempt to use L'Hopital's. Okay. So that's equal to, hopefully, the limit as x goes to 1 of the derivative of the numerator divided by the derivative of the denominator. Okay.
So
Now,
what's the purpose of 0 and 0 in the numerator and denominator?
what's that?
So what's the purpose of writing this 0 and 0 in the
Show
numerator and denominator?
that you show that you recognize the form and that now you're going to use L'Hopital's rule.
So can you go to the previous slide?
Yeah.
Okay, sir. Thank you.
Okay. So now, now what will I get if I put in x is equal to 1?
So you will get 4x divided
4x over 3.
I would
3.
get 4 times 1 times cos of 0, which is 1, divided by
So
3 times the cos of 0, which is 1, right?
1. So 4x over 3, which is like 4 over 3.
4 over 3.
Yeah, so I'll get 4 over 3. Okay, right? Because I've got a continuous function on the top, and I've got a continuous function on the bottom. So the temptation is to just do substitution, right? Right? It's a quotient of continuous functions. But it just happens not to work at x is equal to 1. All right, so then we use L'Hopital's. Okay, let's try this one. The limit as x goes to 1 of a polynomial divided by a polynomial. Okay, so that's a continuous function divided by a continuous function. I'm tempted to use substitution. But if I tried to use substitution, I would get 0 over 0. Okay? So what I do, I say, well, I get the form 0 over 0. So I'm going to use L'Hopital's rule. So I get, now when I take the derivative of the numerator, I get 4x cubed minus 6x squared plus 2. And I take the derivative of the denominator, I get 2x minus 2. Now if I put in x is equal to 1 into these two functions, I would still get 0 over 0. But it's not, I haven't been wasting my time because I have reduced the degree of the polynomials. Okay? So now I apply L'Hopital's again because I had the form 0 over 0. And I get limit as x goes to 1 of 12x squared minus 12x over 2. So now the denominator, now I'm not going to get 0 over 0 anymore, right? Because the denominator is a constant. Okay? So now I've got a continuous function over a continuous function where the bottom function is not going to 0. So now I can do simple substitution. If I do some sort of substitution, then this will come out to 0. Yeah, there's a question?
Yes, sir. I just wanted to ask, what is the point of doing this? Like, this seems pretty pointless right now, especially for this question.
For this question?
Yes.
Well, yeah. Well, okay. You could probably do the question. Maybe you could do the question in other ways. But I'm just trying to illustrate the use of L'Hopital's rule. I'm not taking particularly difficult problems. Okay. There's another question?
Yes, sir.
Yeah.
Sir, I wanted to ask that why weren't we taught L'Hopital along with the limits when we
Because
were
we
doing
didn't
the
know
derivatives?
derivatives. We didn't know derivatives at that time, right?
So, but it came in the mid. It was expected that we should be knowing it.
No, it didn't.
Yes, I think it did.
Right?
The TAs were pretty clear that you could solve any question without L'Hopital's rule during
Yeah.
the midterm.
You're right.
But it was much easier to use it.
Maybe, but you weren't required to know it, right? Okay, let's try this one. The limit as x goes to 0 of inverse tangent of x divided by x. So what's the inverse tangent of 0? 0. Okay, so once again, this is a problem where you get 0 over 0. So you say, all right, fine, let's use L'Hopital's rule. Derivative of arctangent of x is 1 over 1 plus x squared, and the derivative of x is 1. So we have the limit as x goes to 0 of 1 over 1 plus x squared, which is, now you've got continuous functions on the top and the bottom, which are not going to 0. So you can just do a substitution. Right? So 1 plus 1 over 1 plus 0 squared, which is equal to 1. Are there any questions about this one? Okay. All right. How about you tell me the answer to this one then? The inverse sine of x minus pi over 2 divided by the root of 1 minus x squared. I want the limit of that function as x goes to 1 from the left. Okay? Right. Okay, somebody give me the answer.
Minus 1.
Okay, let's see. Okay, so first of all, what's the inverse sine of 1? Pi over 2, because sine of pi over 2 is 1, right? So you would get, if I naively put in x is equal to 1 on the top, I would get inverse sine of 1, which is pi over 2, then minus pi over 2, that would give me 0. And at the bottom, if I put in x is equal to 1, I will get the root of 1 minus 1 squared, which is 0. So this would have the form 0 over 0 if I tried a substitution. Okay. So then I will try L'Hopital's rule. I write 0 over 0 in square brackets to show that I understand that I get the form 0 over 0, and that now I intend to use L'Hopital's rule. So that's the limit as x goes to 1 from the right. What's the derivative of arc sine of x? It's 1 over the root of 1 minus x squared. Derivative of a constant is 0. And the derivative of root of, well, that's 1 minus x squared to the 1/2. So its derivative is minus twice x root of 1 minus x squared, so on. And so you would get minus x over the root of 1 minus x squared. Now the root of 1 minus x squared is common in both numerator and denominator, so you can divide those out. And now you get something that you can work with. The limit as x goes to 1 from the left of 1 over minus x, which is equal to minus 1. Okay. All right. Let's try this one. The limit as x goes to positive infinity of x times the sine of 1 over x. Okay? Now, if I if I pretend that infinity is a real number and I substitute in here, what do I get?
0.
I get the x goes to infinity, right? And the sine of 1 over x goes to 0. There's a question?
Sir, can you move to the previous slide? I just want to match my answer for that.
Okay.
Yes, sure. Okay. Thank you.
All right. Are there any other questions about this question before I go on? Okay. All right. So substitution would give us this indeterminate form. The first term is going to infinity, the x is going to infinity, and the sine of 1 over x is going to 0. So I get this indeterminate form 0 times infinity. Okay? L'Hopital's rule does not handle that. L'Hopital's rule deals with 0 over 0, or it can handle infinity over infinity. It doesn't know how, it doesn't help you with 0 times infinity. But what you can do is you can do some algebraic manipulation so that you turn this problem into a problem that can be handled. Okay, so this is what you do. The limit as x goes to infinity of x times sine of 1 over x. I will rewrite x times sine of 1 over x as sine of 1 over x divided by 1 over x. Okay, so that's just an algebraic manipulation. I haven't really done anything. Okay. All right. Now, if I let x get arbitrarily large, 1 over x is going to 0 and 1 over x is going to 0. So I would get the form 0 over 0. Now that is a form that L'Hopital's can help you with. So now you apply L'Hopital's rule. And the derivative of sine of 1 over x, you use the chain rule, right? So it's cos of 1 over x times the derivative of 1 over x, which is minus x to the minus 2, divided by, now you need the derivative of 1 over x, it's minus x to the minus 2. Okay. So now I've got a common factor of minus x to the minus 2 in the numerator and in the denominator. So let's take that out. And now I've got the limit as x goes to positive infinity of cos of 1 over x. Okay, now 1 over x is going to 0. So this is cos of 0, which is equal to 1. Okay, is that all right? Yeah, there's a question?
Yes, sir.
Yeah.
Sir, can we do that, question by multiplying by 1 over x and dividing by 1 over x, and sine 1 over x over 1 over x gets to 1, and x into 1 over x gets to 1?
Yeah, there might be other ways of doing it. You might be able to make some in this second line here. I can think of a substitution, for example, that would work. Okay, so quite often when you do a L'Hopital's problem, there are other ways also of doing it. Okay. Now, here's an example where L'Hopital's doesn't work. Limit as x goes to positive infinity of root of x squared plus 1 over x. Right? Let's say I decide to use L'Hopital's rule. What will happen? Right?
The numerator doesn't actually approach infinity, so you can't actually use it.
The top part goes to infinity and the bottom part goes to infinity. So you would get the form infinity over infinity. So in principle, you can use L'Hopital's rule. But if you actually work this out, what you'll see is that you will get an infinite regression. Every time you use L'Hopital's rule, you'll get something that isn't any simpler than the problem you started with. And you would just keep on, if you tried to use L'Hopital's rule, you'd just keep on doing it over and over again, and you would never get to a form where you could actually do some substitution or something to and finish the problem.
So basically you are saying that we'll have to differentiate again and again?
Yeah, you just end up in differentiating infinitely many times without solving the problem. Okay, so this is a case where L'Hopital's fails. Okay.
And sir, how would we identify okay, L'Hopital rule doesn't work here in this
Well,
question or not?
if you keep getting essentially the same problem over and over again, every time you apply the rule, then that means L'Hopital isn't going to help you.
Sir, but over here, when we differentiate the first time, we get a 1 in the denominator. So why does this not work?
Because you've got that when you differentiate the root, you're going to get something in the denominator, which is not going to help you. Okay.
Oh, okay, sir.
Try applying L'Hopital's. You'll see what I mean. Okay. All right. Here's one that you can try. It would take a while to work it out. But you know, you should give it a shot. See how it works with L'Hopital's. There might be other ways. There might be better ways of doing this problem. Okay. Yeah. There's a question?
Sir, can you briefly explain the working of this question? Like what would we do when we try to solve it?
Okay, so the way I would do it is I would divide by x cubed on the top and the bottom, and then avoid using L'Hopital's rule at all. Okay. On the other hand, it's perfectly fine to use L'Hopital's rule, and you might have to apply it several times before you get your answer.
Okay, sir.
Okay. All right. Okay. So in this one, limit as x goes to pi from the left of x minus pi times tangent x over 2. Okay. Now, what's tangent of x over 2 as x goes to pi?
1. Infinity.
It's going to infinity, right? If you think about how there's this asymptote, this vertical asymptote at x is equal to pi over 2, right? Okay. So this has the form 0 times, this has the indeterminate form 0 times infinity. Okay. So the way to do this remember we saw a problem that had 0 times infinity before for the indeterminate form. Okay. So go back, take a look at that problem, see how we worked that one, and try and work this one in a similar way. Yes, there's a question?
So I don't understand why would we get -2 by this? Like if we put pi in the x, so we would be getting 0, right?
No, no, we've got tangent of pi over 2, right?
No, before that the coefficient of tan pi by 2, it's x minus pi. So if we put x is equal to pi in this, wouldn't we get 0?
Okay, but you've got the first term x minus pi, that's going to give you 0. You've got another term tangent pi over 2, which is going to give you infinity. So you have the indeterminate form 0 times infinity.
So then why it's -2?
Well, I mean, I'm giving you the answer. I'm saying here's an exercise. Try and use L'Hopital's to do this, and you should get -2. Fatima has a question?
Sir, could we simply use product rule in this question? Would that work?
No.
Okay.
You have an indeterminate form 0 times infinity. So what you need to do is you need to rework. We had a previous problem. What was it? It was x times sine of 1 over x. You had the same issue. Okay.
So in Hopital's law, we had two functions. One was in the numerator and the other one was in the denominator, and we were taking the derivative of both. But now in this situation, we have like two functions. If we say they all are like together, how can we like differentiate between numerator and denominator?
Well, in this one, you would have to rewrite this function as a quotient, right? You can't.
So can you tell how?
It's going to be tan x over 2 divided by 1 over x minus pi.
That's right.
Then we're going to keep differentiating it.
That's right. Or the other possibility is you should write x minus pi over 1 over tangent x over 2. But you have to rewrite this as a quotient if you're going to try and use L'Hopital's rule. You have to rewrite this as a quotient that's either going to give you 0 over 0 with substitution, or with substitution would give you the indeterminate form
So
infinity.
will this work that if I keep x minus pi in the numerator and if I like put this tan in the denominator as tan inverse?
That's what I'm saying. You should try that and see what
Okay.
will happen. Okay.
Tan inverse is the reciprocal of tan.
All right.
I mean by tan inverse tan -1.
Well, I'm not using the inverse tangent here, so.
There is 1 over 0 always infinity?
Well, 1 over 0 gives you the indeterminate form of infinity, yes. All right. Okay, so there are a couple of more problems in the notes that I think you should try. So try those two. Now, once again, let me emphasize something here. You can't use L'Hopital everywhere. L'Hopital works if you, no, actually, L'Hopital isn't even guaranteed to work. You're allowed to use L'Hopital if substitution would give you an indeterminate form 0 over 0. If you've got a quotient and the numerator goes to 0 with a substitution, and substitution gives you the denominator going to 0, so you got 0 over 0 indeterminate form, then you might try L'Hopital's rule. If substitution would give you the indeterminate form, infinity over infinity, then you might try L'Hopital's rule. So, but you cannot, or you might have forms that look like 0 times infinity, or 1 or infinity to the 0, or 0 to the infinity, things like that. We'll see those a little later on. And then you have to do some manipulation so that you can put it into a quotient which will either give you the indeterminate form 0 over 0 or infinity over infinity.
The answer is 6.
That's not the question. You're not answering the question that was asked. Okay, so, but you must not use L'Hopital's rule until you can get some sort, those two indeterminate forms. It cannot be used everywhere. So let me ask you, why are you not allowed to use L'Hopital's rule over here?
So we simply get 8 over 0. So we
Right, you would get a
require
form
it.
8 over 0, and that's not a form that L'Hopital can help you with. Okay?
Yes, sir. We get straight to the answer.
So L'Hopital, you cannot use L'Hopital's rule over here.
Sir, but sir, this 8 by 0, we have 0 in the denominator, and won't it give a math error?
Yeah. But the question here is why can L'Hopital not be used for this problem? And the answer is that substitution does not give you one of the two forms that L'Hopital's rule can be used with. Okay.
So is there a way we can manipulate this?
Oh no, this one I think is the limit doesn't exist.
Okay.
All right. Okay, so that's it for this lecture.
Sir, what if we apply divide the x with x in the denominator?
You'll still have a problem. I think it still doesn't work.
So the limit for this question is going to be dne?
Yeah, it doesn't exist. Yeah. Okay.
So can you, will you mind like repeating it, that why can't we use this Hopital's law for this particular question?
If you substitute in x is equal to 3, what does x squared minus 1 give you?
So it gives 8.
Right. And if I substitute in x is equal to 3, what does x minus 3 give you?
So it gives 0.
Right. So this gives you an indeterminate form 8 over 0, which is not one of the forms that L'Hopital can be used with.
So you are saying that it should be a determinant form of your numerator and denominator if you want to apply L'Hopital's law.
There are many indeterminate forms, but L'Hopital cannot be used until you have an indeterminate form, either 0 over 0 or infinity over infinity. Here you're getting an indeterminate form 8 over 0 that L'Hopital cannot be used with.
So what if we had like carrying on the discussion of this indeterminate forms, let's assume that we have some sort of uh, vertical or let's say horizontal asymptote in this numerator, then will it work?
You can, like I said, you either have to get those two indeterminate forms, or you have to be able to manipulate the function in such a way that you would get those two indeterminate forms, as we saw before with 0 times infinity.
So if we have we have numerator and denominator, if only one, either it could be the numerator or it could be the denominator, only one side is indeterminate and the other one is like determined, then the same principle applies, the same principle holds.
No, you can only apply it to two forms, the two forms that I've shown you. You cannot apply L'Hopital's rule until you can get those two forms.
Okay, sir.
Okay. Right. Are there any other questions?
Sir, I have a
for
question.
this,
Yes.
You can go first.
right, thank you. Sir, in this example, we get 8 over 0, and can't we just manipulate it to get 8 out of the limit and get 0 over 0 inside the limit?
No, I don't think so. I mean, you can try, but I don't think you can do it.
I mean, it's a general question like, can we manipulate 8 over 0 to get 8 times 0 over 0?
No.
Why is that?
Well, 8 times 0 would give you 0, right? Wouldn't give you 8.
Yeah.
Yeah.
Over 0 will also give us like say 0.
Sorry, what's the question?
No, sir, I got it. I got it.
All right, there was another question. Yeah, speak up.
Sir?
Yes?
Sir, in this case, we can't use L'Hopital rule, but you have specified another case where L'Hopital rule fails is when the derivation gets unlimited and you can't reach to the final answer, right?
Yeah.
So there are two cases where L'Hopital rule wouldn't get us the answer.
Right. Right. We saw one case where just applying L'Hopital's rule over and over again will not get you any closer to the answer. And here's a case where there's no way to manipulate this expression into a form that L'Hopital's can be applied to.
And if we get an intermediate type equation, we have to manipulate it to get to 0 over 0 or infinity over infinity and then apply L'Hopital, right?
Right. If you have another indeterminate form, then you're not allowed to apply L'Hopital's rule until such time as you can put it into the form 0 over 0 or infinity over infinity. Okay. Right. Are there any other questions? Okay.
Yeah, I had one.
Yes?
When will we get our mids back?
Hmm?
When will we get our midterms back?
I don't.
When we will get midterms back?
I don't know. I mean, if it was up to me, I'd just failed a lot of you for cheating anyways. So.
Sir, but there was it with honesty.
So your voice is breaking up?
Sir, I was saying there were so many people who did it with like full honesty. who like
Yeah.
prepared it for it.
Yeah, but which one of you? How do I know which one?
Marco Polo.
Sir, but this
Most of us
scenario was
followed.
No, I'm not saying that I'm going to fail all of you. I wouldn't do that.
Sir's kidding, guys. Calm down.
Right? I'm not going to do that. I'm just saying that there are issues with this exam, so I can't say exactly when it'll be marked. Fatima has a question.
Yes, sir. Sir, are these chapters going to be the ones tested in the mids? Are those going to be tested in the finals too?
Yeah, at least some of the material from the final is comprehensive. It covers everything in the course.
Okay.
Okay. All right then.
So
Yes.
I can say for myself that I did it with the honesty.
Okay, fine. I believe you. Okay. Are there any other questions?
Sir?
Yes.
Sir, just one question left. Sir, is there any so if we have an intermediate form 0 into infinity and we can't make it to 0 over 0 or infinity over infinity, we
Yeah.
can't apply right the
That's
L'Hopital.
right. That's right.
So will there be any? Are there any questions in which we can do that?
Well, here's a question, right? I mean, you can't put it into those two forms, so you should not use L'Hopital's rule, and you should make some. And in this case, I think the limit doesn't exist, so you should make some argument as to why the limit does not exist.
Okay, sir. Thank you.
Okay.
Sir?
Yes.
Sir, can you go over the slide that you asked us to solve, which had an answer -2?
Okay. Yeah, here.
Yeah, this one.
Yeah, okay. So the first term, so there's two functions which are being multiplied here. The first term, if I put in x is equal to pi, would give me 0. The next term, well, it's undefined by pi, but very close to pi. The tangent is hitting a vertical asymptote. It's going to infinity. So this has the form 0 and 0 over infinity. So, sorry, 0 times infinity. So you can't use L'Hopital's with it. So what you might do instead is you might write it as tangent of x over 2 divided by the reciprocal of x minus pi. Then it would have the form infinity over infinity. And then maybe you can apply L'Hopital's rule and see what happens. Okay.
Yeah, okay.
Okay. All right then. Any other questions?
Sir, the previous slide 43, can you go with that?
Slide 42?
This one. Yeah, no, this one.
This
Problem 7. Yeah.
Yeah,
I'm
okay.
using the L'Hopital rule again and again, but it's not solving. So can I solve it directly? Like it's rigorous calculations.
Yeah. Yeah.
So can I solve it directly?
Right. Yeah. So what you would do, okay, so what I would do is I would divide the top and the bottom by x cubed. Okay?
Yeah, I know that. Like, can I solve it directly without using the L'Hopital rule? Because the calculations are going really complicated.
Yeah. Yes. I'm saying in order to avoid using L'Hopital's rule, what I would do is I would divide everything through by x cubed.
Okay.
And remember that when you take the x cubed inside the square root,
it becomes x6.
It should become an x to the 6th, right? And then you'll get things that are fairly easy to manipulate, right? Okay.
Thank you.
All right.
Thank you.
Any other questions? Yeah, Fatima has a question.
Yes, sir. Another one. So if we get 0 into infinity, then we manipulate it, तो फिर हमारे पास आ जाएगी limit?
No, there's no guarantee.
Okay.
But let's see, where did we do this? Yeah, so we did this here, right? We had 0 times infinity, right? And then we wrote it as a quotient, right? L'Hopital's works with quotient, a function divided by a function, right? So we rewrote this as a function divided by a function, which could actually work for us.
Okay.
Okay. All right then. I will see you on Thursday.